Hello students. In this session we are going to discuss about assumptions of linear regression. So let us begin with what exactly is linear regression and how does it work. Linear regression is a straight line that attempts to predict any relationship between 2 points. So basically if you know the speed of a vehicle, then will speed help you to determine the time taken by that vehicle to reach a particular distance? The answer is yes. So that is what linear relationship talks about. That a straight line that attempts to predict any relationship between 2 points. Now, this prediction is expected to be in a statistical relationship rather than to be deterministic one. That means that let's say if somebody goes for, let's say, a is the speed and b is the time it is taking, and let's say p is the speed and c is the time it is taking. So it should not be like a table which is given and just we are referring a value from the table and we are giving the prediction. It is not like that. This comes from a statistical relationship. Let us understand more about it. Here you can see a simple linear regression where we have one variable which is the predictor, or which basically is independent one, and the other variable is dependent on this particular variable. So what will happen in this particular case? When this variable is going to increase, the other variable is also going to increase. When the independent variable is going to decrease, the dependent variable is also going to decrease. The relationship can be opposite as well. The independent will increase and the dependent will decrease. So even in that case, it is simple linear regression. It shows relationship between two variables. Now there are assumptions of linear regression. The assumptions are that the two variables should be in a linear relationship. All the variables should be multivariate normal. There should be no multicollinearity in the data. There should be no autocorrelation in the data. There should be homoscedasticity in the data. There shouldn't be any heteroscedasticity. Let me help you out with these things. To help you out, I will just try to work on the paint window. Let us start with the first one. The first one says that linearity. The linearity basically is, let's say, this is our y-axis and this one is x-axis. So here we have some data points. Now we need to see that how these data points are organized. So you can see that how these data points are organized. If I wish to have a line fitting these particular data points, is it possible that a line can fit or pass by? And that too I want one straight line to fit into it. So the answer is yes. I can have a straight line which can fit within these points. But let's say if I am taking a very similar, this particular similar graph, if you see, this one is having a little difference, and that difference is the data points which we have, they are distributed like this. So you can see that the data points which we have are distributed in a different manner this particular time, right? So they are having some different manner, you can see here. Okay, so now what is going to happen in this case? Will we be able to draw a straight line? The answer is no. We won't be able to fit in a straight line over here. This is the property of linearity, that we want data should have linear relationship. That is the first case we actually want. Now second one is normal distribution of the data. Now what does this normal distribution tells? This normal distribution is about the error. Now we have the error plotted in a distribution. So when we are plotting error, then in that particular case, it should be normally distributed. So something like this. So here you can see, so it should be normally distributed. That is what is expected. So if you want to find it out, then basically this is one way where you can see that it would be normally distributed. And there could be other way also. And the other way would be that yes. So there could be other way also. This is graphical way. And if I see this graphical way, you can see that it is normally distributed. The graph you can see. Okay. So normal distribution is bell-shaped curve. It is similar to that. But on the other way, if the relationship is not like that, let me draw in a separate way. Let's say if the relationship is something like this, then basically it is not normally distributed. So it has to be normally distributed. The data has to be normally distributed. Then we can also go for performing the KS test or Shapiro-Wilk test. And if we are getting a value of p-value, we are getting 0.05 or greater, then in that case also we can say that there is no much deviation from the normal distribution. So this is what we are talking about, the error or the residuals. Now the next point we have is homoscedasticity. This homoscedasticity should be present. Homoscedasticity. So this homoscedasticity, if you see, the variance of the errors or residuals should be constant. That is what is the homoscedasticity. So now when we are plotting errors, in that particular case, these errors and the output variable should have no relation. So let's say this is your output, okay, and your error should be, like anywhere. They shouldn't basically show any kind of a relationship with the output. That is what is homoscedasticity. But if this is not the case, then second thing would be heteroscedasticity. In that particular case, you will be able to see that in a particular graph, the kind of distribution you will see would be something like this. These will be the data points of the errors. So we need homoscedasticity. We don't need heteroscedasticity. Next assumption we have is multicollinearity. So multicollinearity means we have a feature x1 and we have a feature x2 and output is y. Now basically if change in x1 leads to change in x2, okay, this is multicollinearity. This is multicollinearity. Okay. So change in x1 leads to change in x2, which should not happen. Like x1 and x2 should both contribute to y, but x1 is also contributing to x2. That is basically multicollinearity. So these are certain assumptions of simple linear regression. Before we start with any experiment, any implementation, we actually check these assumptions of linear regression. I hope you understood this concept, and in the upcoming sessions, we'll also see implementation. Thank you very much.